good. Okay. And this? No. Louder this way. Try to hold my head up. So today we're going to sort of complete the story by, if I can find some chalk, by designing a kind of filter or event meter, whatever is a good name, for an arbitrary event E. And although I think when you see how it's done, you'll see that the technique is quite general. I'm going to illustrate it in the simplest case that I could think of, which is this two-site hopper, which I described abstractly before, and which we'll now describe concretely in terms of a particular optical setup, or that is, I mean, a setup using photons and beam splitters, very similar to what we already saw in the case of the Mach-Zehnder, but in this case it'll be slightly different, but using the same optical elements. So this is so let me draw a picture. Let me draw a picture of the setup that I have in mind. I might mention that if you're interested in seeing something similar to what we've done already, in some examples in which path integral methods are applied to deduce, in the particular example I'm thinking of that I'm going to refer you to, we analyze the EPR type correlations in terms of very similar to this. That's a paper that I wrote with S. Sinha several years ago. So this S is remarkably uninformative when it's followed by Sinha. So this is actually this is one of two Sinhas, both with S, who are actually sisters with whom I've written papers. So even but if it's Sukanya, then it's relatively unique. So this is just an example you might like to look up, just to see another example of path integral way of analyzing something that's traditionally associated with one of the paradoxes of quantum physics. So the example, well, we're so good about cleaning the blackboard here that it's gone. Anyway, but I'll draw it again. So we'll have a source emitting a photon, and then we'll have, let me draw, I think I started to draw this before, a succession of, what do I want to do? I want to put this. And a succession of beam splitters, which I'll draw the beam splitters now in red, it's exactly the same thing we saw in the example of the Mach-Zehnder. And then any number of these. And then in this case, we will have some opaque mirrors to just reroute the photons. So these are opaque. These are just mirrors. Okay, so this is, I think I've got all the possible trajectories here. I remind you that the way the beam splitter works is that, I mean, the normalization we're using, the convention, is that the phase convention we're using is that if the particle goes through, it's an amplitude of 1 over the square root of 2, and if the particle reflects, it's an amplitude of I over the square root of 2. You can easily convince yourself that if you think about this as a 2 by 2 matrix, you can convince yourself that it's unitary. And in fact, up to phase convention, it's the most general unitary matrix. So in other words, every beam splitter with some phase convention, if it's a 50-50, one can be modeled like this, okay? And then it's convenient to label the beams 0, 1. So, a path will basically, or history will just be a succession of which beam the photon was in each possible location before and after each beam splitter. Oh, I left out a mirror. I left out some mirrors here. And so because of the way this is set up, it's convenient to label them. This is beam 0, the upper beam, but then here the upper beam, the lower beam should be, I'll call 0, and here the upper beam. Just a convenient convention, and this will be beam 1 and beam 1 here. So a history that looks like, as before, history will be always a bit string, representable as a bit string. It'll always start with 0 because that's the beam in which we released the photon. So a history like 0, 0, like I've drawn here, 0, 0, 1 would be going along here, 0, 0, 1, right, and so on. So I think it's clear how this is set up. And as before, I'm in writing the amplitude, when we come to compute the amplitudes, which we will in a second, as before, I'll neglect all the amplitudes that are the same for all possible histories, like the amplitude to propagate from this mirror to this mirror, or the amplitude to reflect at each mirror. Okay. I was going to introduce a kind of Hilbert space notation for this beam splitter, but I think it'll be more, it'll be wiser to skip that. And if there's any time left at the end, we can see, which never happens anyway, we can see what, if anything, we want to go back to, such as the three-slit paradox antinomy, for example. So given this, now an event, given this whole setup, an event, as before, is a set of histories, which I could call gamma 1, gamma 2, gamma 3. When we come to do the general case, I'm going to introduce a slightly different notation for the set, because it just makes, the notational complications are so great that anything that simplifies them a little is worthwhile. Maybe it can be simplified more than I've been able to do. But in this simple case, anyway, we won't need this more complicated notation. So this is a particular history, a set of, say, a particular event, a set of n histories. And the question that we're now facing is, can Orbashi measure mu of E? In other words, do experiment to determine mu of E in her optics lab. Or of course anyone else. Is it possible to set up a protocol to measure this? So let's remember what is the usual situation. How you measure, how you ascertain, let's say. I say measure because that's kind of fun. The title of this series was the quantum measure and how to measure it. But I don't want to suggest anything special by the word measure. I don't want to suggest, for example, this, what I was calling Copenhagen-Noether's set of paradigm. So a more neutral word would be, this is not too small, can she find it out? Can she ascertain it? Is there some experiment that she can do without knowing what the beam splitters here, without knowing what happened between one beam and the other, treating this as a black box? Can she work out what is the measure of that event? Then of course one can compare it with the theory of the beam splitter and see what it agrees. So it would be an experimental test of the rules for computing the quantum measure, the path integral rules, or double path integral rules, if you like, for computing the quantum measure. So we're trying to, so let's think of a simpler case, and as a kind of reference point to see what we can do in this situation. So let's take a much simpler case where we have some diffraction or something like this, and we have a detector. And the only event we're interested in this simpler case would be that the photon, tell me if I'm writing too small again, arrives at D. Okay. So that's a particular event. It's a set of photon trajectories. In this case, how do we do it? We put a detector here, and we have a sort of counter, let's call it, which clicks when the detector goes off, and so we have arranged it so that the counter clicks if and only if E happens. Now, when I say it happens, I'm already getting into hot water. I'm getting into dangerous ground because I'm really attributing some happening to the micro world, which is a controversial thing to do. However, I think it's not very controversial to say that if you put a photon counter here and it clicks, that probably the photon did arrive at that location. But that's already going beyond pure phenomenology, pure operational statements. In this case, in a kind of harmless way. If this was a classical event, classical histories, then there'd be no controversy at all in saying that this is true. So then, having set such a thing up, then the quantum, in this case, quantum measure, or in the classical case, the classical probability, is just the probability of this click, right? So there's a direct relationship between, I mean, if you want to know what fraction of the photons came here, assuming you have a very efficient counter, you just ask, how many counts did I get here compared to not getting counts here? Once I count the number of photons that are emitted, right? So it's so the mu of E in this case, this is what I called before a terminal event, and it's also what I called a instrumental event. So it fits into two categories, in either of which the quantum measure can be interpreted directly as a probability. So that's one thing. There's a direct relationship between the click probability and the measure of the event we're trying to ascertain. And the second thing that's here is that if this was an ideal, if this detector was an ideal filter, so let's say the detector D was an ideal filter or detector, then we replaced, if we were dealing with the usual kind of story, we would replace the wave in which we work with a wave function. We'd replace the wave function with the collapsed, wave function. Usual, that's the so-called Luther's rule, the usual reduction of the wave factor. Now, an ideal a photon counter is very far from an ideal filter. It destroys the photon or it absorbs the photon or something. So it's not a good model for that. And if you want to think of a good model for that, maybe a polarimeter is good, or something, or even just a single slit, right? I mean, instead of putting a detector here, you put just a slit and you ask, did the photon make it through? Then you haven't destroyed the photon. You'll have to detect it later to make sure that it did make it through, but you haven't destroyed it. So if you regard that as a kind of, this one won't click, unfortunately, but it will reduce the wave factor in the usual way. So I think that's all very familiar. I'm saying that to see in what way we're going to deviate a little bit in this more subtle situation from this kind of arrangement. So what we'll find is that there will be a direct, so I will design some sort of thing that plays the role of the detector. It'll be also considerably more complicated setup. It'll involve several ancillas, and as many ancillas as there are beam splitters here, and it'll involve some certain kind of coupling among the ancillas, and then finally a coupling of the ancillas to the thing that clicks. It'd be just another ancilla. Yeah. Oh, this was the way, just the quantum wave function. That's right. So yeah, I'm drawing exactly. I'm drawing to it. So I'm saying, let's go back to what is more familiar. Not. I mean, it's true that I talked about the measure here, so it's kind of mixed metaphor or something. But I just wanted to say that there are two aspects of a filter or a detector that we might hope to realize in this more general situation. The first one is that the probability of it registering an event is directly related to the measure that we're trying to measure. And the second is that if it does register that that event happened, then that has predictive content, and it tells us, we can use that to make further predictions about what may happen. And the way that we use it in the traditional way, so this is maybe I'll call it, I've been calling it the Copenhagen, this second line, call it Copenhagen Luders, for lack of a better term. Maybe there is a term for this, I don't know. Orthodox textbook, I don't know what to call it. So that second bit, yeah, the second bit here is, as you say, within that. So what we will see is, I'll say, I was just about to say, what we'll see is that in this more general setup, with the ancillas and the basically with ancillas, that there will be a final click event that can or cannot happen, which will just mean some final ancilla will either be in the upper beam or the lower beam. If it's in the upper beam, say it did happen. If it's in the lower beam, that counts as not happen, as not a click. Upper beam is a click, lower beam is a non-click. With that setup, we'll see that the probability of a click will be directly related to the measure of the event that we've designed the filter for, or the detector for, but it won't. But there will be it won't be inequality anymore. There'll be a factor of proportionality. That's the first thing. Specifically, what we'll see will be that in the more general case, we'll see that mu of E is not directly equal to P, but it's got it backward. It'll be the probability. No, I got it right. It'll be the number of histories in the event E times the probability of the click. So depending on which event you're looking for, this conversion factor will be different. The second thing, this gets to what Urbashi was asking about. The second thing, it will be a kind of ideal filter. Maybe I should call it a quasi-ideal filter. What will happen is that if it does click, we will be able to, so to speak, condition the amplitudes, have a new set of conditional amplitudes for the path integral for a subsequent event. And that will be the history's analog of this reduction of the wave packet, which will mean including in the history space only those histories that belong to E. So the effect of detecting E by a click will be that it's sort of the most obvious, straightforward thing. It's the same thing you would have done even in classical inference, if you're doing classical inference, will be that henceforth in doing your computations of probabilities or more generally measures of events, you just throw out the histories that don't belong to E. Okay. So that's if you like, that's the histories-based analog of this Copenhagen-Luders rule. And we'll see that I mean, we won't actually see because I won't have time. I'll claim for you and leave it as a homework that that's the case. But I just wanted to emphasize that there's sort of two aspects to what an ideal filter does in the usual situation, and each of those aspects will have an analog here, but in a way that's a little bit more subtle. And one thing that I should also stress here is that if you have a truly ideal filter, or what people call a non-demolition measurement, I think that's another language that gets used in this context of measurement theory. If you have a truly ideal one, you also learn something. If the counter doesn't click, you learn just as much. Then you project onto the orthogonal complement of the state psi for which the counter was looking. That piece will not find an analog in this setup. So that's the sense in which I was saying that this is a quasi-ideal filter. It's somewhat less than ideal than what one is used to in the paradigmatic projection operator and orthogonal projection operator. Okay. So how does this work? So all I want to do now is design it in 3 stages. So first we're going to do the simplest possible case, which is so simple that you would never think to actually design an experiment to do this. Well, you wouldn't think to design such a complicated experiment as we're going to do. You could do something much simpler. It's just a case in which the whole event is just one history. So in other words, just looking for one particular history, which I'll call gamma as always, and see how we can do it in that case. If you think about what you would probably do if you weren't thinking ahead to the more general case, you would just put a detector here, an ideal. You'd have to put one of these ideal kind of detectors here, 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 which you could do basically just by blocking off the others beam that you weren't interested in. That's essentially what happens in kind of 3 experiments that have been done, that were done originally at IQC. Anyway, and then you would just find the probability of the photon making it through that maze, and that would be the measure of that particular history. So that's not what we're going to do here. We're going to do it in a way with the ancillas, just to warm up for the more general case. The second case I'll look at is where the event, again, is very simple. It consists of only 2 histories. So E is equal to, say, gamma 1, set containing gamma 1 and gamma 2. Specifically, in fact, I wanted to have a particular history, just for concreteness. We don't need more than 2 beam splitters here to illustrate this. So this will be this particular event, 0, 1, 0. In this case, gamma 1, I'll choose to be 0, 0, 1, and gamma 2 to be 0, 1, 1. Why have I done that? Well, I've made the final beams be the same so that we'd have interference. So this is the first case in which we would see the effects of interference. So in this case, we have interference. We'll also see here the role of what's often called the quantum eraser. We'll see something like that going on, although we don't need that word, but that's for those who know what it is, it'll help to understand what's going on in this setup. And then we'll also see where why the probability of click is not directly the measure, but it is related to it by a factor. So we'll see this factor of 2, which is a factor of the number of the cardinality of the event, which in this case is, of course, 2. And then the final case, I may suggest to do as a homework. I mean, I will suggest that you might like to look as a homework. I won't do this case, again, gamma 1 and gamma 2. Same number of histories, but in this case, let's do some without interference. Oh no, in fact, we can do this even more simply with just one beam splitter. So the histories will now be of length 2. And of course, it always starts in 0, so really it's as if the histories are of length 1. So just consider those two. In this case, there's no interference because the final beams, the final outputs, final outcomes are outputs, outtakes, outcomes. Okay. The final outcomes are different, so there's no interference. Nevertheless, if you use the same general scheme, in fact, in this case, there's nothing else that can happen because I've only put 2 beam splitters. So in fact, this event is the whole of omega. So we know that its measure is 1. It's the whole of the history space. Because n is equal to 1 in this. Well, if I had labeled the histories from 1, let me not say that. I think I might have used n for 2 different things. I just mean 1 beam splitter, that's all. Yeah, so something else is 1. 1 beam splitter. And so it's useful to see that despite the fact of there not being interference, you'll still get the same factor of 2 if you mimic the same scheme that we're going to illustrate in 1 and 2. And then in 4, so this is homework. And then 4 will be the general case. So this will require a significantly more complicated notation, so I want to do these where it's more, hopefully more transparent what's going on. If you want to think of an example of the general case that's pretty general, consists of just 3 so I've tried to design it so that there's both an interfering pair, these 2, and a non-interfering pair. This one with either of the 2 others, and there's something in common between the 2. This is about as general as I could think with 3 histories. So this you can do for fun. I will not do this explicitly because writing out all the algebra is already so complicated that I don't think you learn anything you won't learn from seeing the general case. So that's sort of what we have ahead of us. And so let's go with the single beam splitter. I mean, with the single history. The event consisting of a single history. Where did it go? Right. From this, we can also so we're doing this case. And I'll take the opportunity also to go through a little more carefully just once again, how the amplitude, how the quantum measure is actually computed. So one other thing that I have to say that I didn't say yet is that I'm going to introduce an ancilla. As I said before, I'll introduce an ancilla for each beam splitter. So I ought to really draw this in here. I'm not sure how to represent this, but this is the first ancilla. This first ancilla asks, it's going to be in quantum information language, it'll be a controlled NOT gate. But if you're thinking of actually setting this up on a quantum computer, but it's just something that will register whether the particle is in beam 1 or in beam 0. So after the ancilla is coupled, the ancilla itself will be a 2-state system, or a qubit, let's say, which I'm not going to model the ancilla. That's another interesting, I've not even tried actually, but I'm sure there's a fairly simple way using these same optical elements to model what the ancilla does and how it couples. We'd have to put in more beam splitters here. I don't know, maybe someone has already. I'm sure many people have already done this because people designing quantum computers need to be able to do this. But anyway, the ancilla will be coupled in such a way that if the particle was in beam 1, the ancilla will be in its beam 1, and if the particle is in beam 0, the ancilla will be in its beam 0. So the ancilla itself will have a history space. But the ancilla is something very simple. So let's call it A for ancilla. It has, let's say, a source. But it's coupled. The important thing is that it's coupled into the other system in this way. But it can emerge either in beam 0 or in beam 1. And the coupling is to be chosen so that this just mimics what the photon has done. Okay. I mean, is it clear? Or if it's not clear, hopefully it'll become clear when we go through the calculation. Is it relatively clear what I'm saying? It's strong, except it's strong. Except that it's strong. Yes, aside from the fact that it's strong and not weak. We could call it a pointer state too. But it's not a pointer in the, if by pointer you mean something macroscopic in the lab which decoheres and never interferes with anything else, then it's not, because we have to take these ancillas. See, if we were just, we'll have another ancilla for each set of beams. This diagram's getting kind of complicated, but let me try and indicate something. One ancilla per time step, exactly. Someone who doesn't care what was going on with the beam splitter and only is interested in the history as expressed in which beam the particle was in after it emerged from one beam splitter and entered the next, they could view this, they could view each one of these beam splitter setups and mirror setups as just a black box. In this case, it's a red box. They could view it as some sort of red box. They just know that the photon enters in one of these two beams and it emerges in one of these two beams, and that's all they really have access to. And that's all that the ancilla is looking at. It's just going to register which beam in each case. So yes, so for each black box here, there'll be one ancilla to say, and we won't bother with the first one because we know which beam it's in. That's an initial condition. What was I going to say? Yeah, so Urvashi had asked about the pointer. So we could go now and say, just observe each ancilla and see which beam it is. You could do that, but of course that would completely disrupt future interferences. It would be like looking which slit something had gone through. So if you were to just do that, you would end up decohering all the different, you would destroy all interference between different paths. You would determine for sure the path, but you would destroy the interference. That's good enough if you're only interested in an event consisting of a single path, which will be our starting case, but it's certainly not good enough in the general case. And so the whole subtlety of this setup is what to do in the more general case, where you don't want to destroy all the interference. You want to let all the histories in E interfere among themselves, because only in that way will you get the right value for the measure, the quantum measure of the event. But you wouldn't like them to interfere with the ones outside of E. And in fact, you wouldn't like the ones outside of E to play any role. You would like to filter them out, so to speak. And that's what this is designed to do. So you could think of it as a kind of two-stage process. First, you get full information, transfer it to the ancillas, then you play around with the ancillas in such a way as to keep what you need and no more than what you need. So the ancilla is a memory, indeed, and then you want this to be a kind of selective memory. Certain things you'd like to forget, and certain things you want. We all have some things we'd like to forget. So if we could use this quantum eraser, we could forget it. So you may, as I said, those who are familiar with it in the case of two events, the second case, you may recognize this quantum eraser in operation. So, okay, so let's start with case one, the particle alone. Oh, and maybe I can say one more general thing, which is sort of implied it, but I didn't say it explicitly, which is that this whole procedure will be kind of a three-stage operation. The first stage is coupling in the ancillas. The second stage will be coupling the ancillas among themselves and to the final ancilla, which is just to click or not click. And the third stage is kind of trivial. It just means to observe whether you got a click or not a click. If you were doing it in a laboratory, you would need to recognize that third stage. And in the two different stages, you have different spectators. So in stage one, this counter is a kind of spectator. You just couple in the ancilla. I mean, the counter itself is another ancilla, but I'll just call it the counter. So it'll be another two beams thing like this. But in stage one, just the main ancillas, not the counter, are coupled to the system of interest. Let's call it the photon, the particle. In stage two, the system of interest, the particle, is completely a spectator because we've already remembered everything we need to remember. And we're just manipulating the memory that we have. So it's important to remember that in the second stage of the process, which is where all the complications come, that the particle is no longer involved directly. Nevertheless, because of the usual way that entanglement works and so on, when you get a particular result, it does tell you something about what the particle did, and it does tell you how to correct the path integral for the future in the generalization of this Lüder's rule, which means the histories-based version of this Lüder's rule, if you like, which means to retain only those histories that belong to the event E. So that's a sense in which, just to repeat, the sense in which this scheme can be regarded as a filter or a detector for E. So let's look at this simple case and analyze it. First of all, we want to know what is the measure that we're trying to measure. So since I'm going to have two measures now, I have to change the notation a little bit. There's first of all the measure of the event that we're trying to compute, and that has nothing to do with ancillas. It's just for this particle and the beam splitters. But then when we couple in the ancillas and so on, we have a bigger system, and it will also be a quantum system, and it will have a history space, and it will have its own measure. So I have to distinguish the two measures. So the particle alone, which is what we've been calling mu so far, because we never considered the ancillas, I'll put as sub-zero. So the measure, this is a measure of the particle system alone in its history space. And then I'll just write mu for the bigger history space. So this is, what do I want to call this? Omega naught, I suppose. History space, which is just which just consists of bit string. Of the given length. Which I can't call n, no, I forgot what I don't know, some length. K or some number, the number of beam splitters. And then we'll have a history space for the bigger system and a measure for it, and that will have, I'll just call it omega. And if you think about it, it's omega not, I mean, well, you won't be obvious yet, but we'll see. As I said, the ancillas just copy the information from history. So each history of the ancillas, this is a whole ensemble of ancillas. It's now, well, I better give this a name. Let's call it M. It's now an ensemble of M ancillas, and it's mathematically representable as a bit string of the same length. And then if you want, there's also, so this is the photon, I'll call it, plus the beam splitters and so on. This is the system, if you like. This is the ancillas. Right? It's many ancillas. So I hope the S is visible. And this is just the counter. This will be our history space for the larger experiment. It's the usual story. If you're trying to analyze an experiment, you have to put the instrument into the system. Yeah. Well, we'll arrange a priori, it need not be the same. The ancilla could have a different history from the particle. And in fact, we will see that in the first stage, we will arrange the coupling in such a way that that won't happen. But in the second stage, there will arise amplitudes for the ancillas not to have the same history as the particle anymore. That's involved partly in the forgetting. So at least there's no harm in regarding these two as independent parts of the history. And in fact, we need to regard them as independent parts of the history when we come to the second stage of the measuring process. It should hopefully become clear. Now I've seem to fill up the whole visible blackboard with stuff that probably well, maybe don't need this. Sorry? You think that's okay to use the next one? Is it okay for people over here? Not so good. Okay, let me erase this. I don't think it will. You need some of those blackboards that go up. So let's look at our I hope I did the right one. I did actually do the right one. So this is this yellow one. This is so we're looking at a singleton event, a history consisting of a single, we have only two beam splitters, so we can stop here. And this is the history that we're interested in. So let's find now the measure of that single event. So we're dealing with that case here. So we want to know what is mu of E, and now I've called it mu naught, the history, the measure computed for the system alone. So let's think of how this history develops in time as the photon makes its way through the beam splitter. First, it's emitted in, what I'm doing here is just tracing through how one computes the amplitude. We've seen it at least once or twice before. And then so it's first in beam 0, then in this particular case, it remains, 0. No, I didn't draw the right history. We wanted to go 0, 1, 0. Okay. Is it worth drawing this? Oh, because I forgot to see that this is the first 0. That is the top one. Yeah, I mean, they're all, of course, basically the same. I mean, the same kind of calculation. Just for correctness, so it's supposed to be 0, then it's, I labeled them alternately because so I would be able to use ones when there was no change in i's when there was a change. So, which was the convention we had before. So 0, 1, what do we say, 0? So that's as far as we're going to follow things. In fact, we'll never have the other ones except when we get to the general case. I'll just erase them now, and then it just goes on its merry way and stays forever in beam 0 because we never touch it again. So if it follows this history. So there's sort of two interesting events where it reflects off here and where it, I guess in both cases here, it reflected. So what happened? It was in beam 0. It made a transition. I mean, continued on, emerging in beam 1, which is a kind of transition from this truncated history to this more extended history, and then it made a transition to a still more extended history, which is 0, 1, 0, and then we're finished. We don't bother with, we're not, assume nothing happens after that. So we want the amplitude for this history. What's the amplitude? It consists of the amplitude that it acquires in this transition, which basically means where it bounced off the first beam splitter. So what's reflected, not transmitted. So what is the amplitude? Well, reflected here, right? So we said that the amplitude with reflection is I over the square root of 2. Now it goes on here. So what was it doing? That was the second beam splitter. Again, in this particular case, it was reflected and not transmitted in the second beam splitter. So we pick up another amplitude of I over the square root of 2. So therefore, the amplitude of the whole history, using the usual, I mean, these are the fundamental rules for path integrals that are sort of Markovian in nature. I hesitate to use the Markovian because it may mean different things. But by Markovian, I mean you can build up the amplitude step by step in this way. So that's what we have here. So in this Markovian case, the amplitude for the full history is just the product of the amplitudes for the individual history. So which is just I over square root of 2 squared, which is minus 1/2. And therefore the measure, in this case, in this case there's no interference or non-interference, there's only one history. So we've got the amplitude. So the measure of that history, of that event, which is just the measure of the set containing gamma, is equal to the square of that, which is the absolute square, which is the square, which is 1/4. So mu of E is 1/4 in this case. Fine. So that's what we're aiming. We want our setup to give us the probability of a click being 1/4 or something proportional by a known factor of proportionality to 1/4. In this case, it will be because there was only one history. So I did erase something that I probably needed, which was that the factor of proportionality is the number of histories, as we'll see. I mean, that's how it is for this protocol. Maybe someone can design a better protocol. I'm not claiming that one can't, but this is the best we know. So now let's redo everything, bringing in the ancillas. But I have to make convention for the ancillas history space. So let me put that over here. So omega ancilla. Abstractly, it's again just a bit string, but this bit string has a different meaning now. It's not subsequent portions of the history of a single ancilla. It just represents what each separate ancilla does. So like here, if you have, say, 3 ancillas, the history of the photon is what it did successively in time. The set of the ancillas, the history space of the ancillas are a separate history space. It's a product, really, of one history space for each ancilla. And what the ancilla can do, as here I had that picture of the ancilla, is it makes a transition into one of 2 beams, 0 and 1. And it starts, I'll call it, since I really don't care what this is, a 0 or a 1, I'll just call it R for ready. So the ancilla starts in the ready beam, wherever that is, and then it ends up as 0 or 1. So an ancilla history, a particular ancilla history, is either, it only has one of 2 possibilities. It's either R0 or R1. That's all the history can be. And then so this is, I don't know a good notation. This is omega 1. This is, I'll call it like this, omega 1, meaning the history space for a single ancilla. Okay. And then the history space for all the ancillas, of which there were m, we said. I'm just saying this hopefully to make the notation clear. That'll be omega 1 ancilla cross omega 2 ancilla cross. In other words, you have many of these, one of them for each beam splitter, and each one of them makes a transition like this. So a typical ancilla history could, a typical element of the ancilla history space could look like this: R0, R1, R1, whatever. Okay. So it's just what each ancilla does. In fact, these do happen in some sense chronologically in some order, because the first ancilla couples in before the second ancilla and so on. But when the ancilla is finished doing its work, at least in stage 1, it just comes out in this beam and it doesn't care. Then there's another ancilla somewhere else that comes out in its beam. So is the picture clear? Yeah, let them be all the same. In fact, since it's always the same, in a second I'm going to stop writing them down because it'll make it easier to write things. But I'll keep them just for, hopefully for clarity in the very first step. So now we're redoing the same calculation, but now we want to compute. Yes. Yes, I'm absolutely, yes. It should be there. So the phase change from the mirror should be there, and the phase change from propagation from one mirror to the other should also be there. But if I didn't make a mistake, those amplitudes are the same for all the histories. So if you like, you could imagine some big amplitude in front of everything that I write down. Okay? As long as that's a pure phase, since it reflects with probability 1, with certainty, you know, it should be, in order for that to be unitary, it's just a pure phase. So there's some big pure phase sitting out in front of everything that I write. When I come to compute measures, I take absolute squares, or wherever it is, and that big phase will drop out. So but strictly speaking, yes, those phases need to be, it's a global phase. It's global, but it is really there. Yes. No, it's not. That's the point. The ancillas, the ancillas are not concatenated. They're completely independent. So this one has its own preparation, and then the next one, which I didn't draw, has its own preparation. They're completely independent at this stage of the measurement. That's one of the crucial points. Then at the second stage, we'll start coupling them to each other, but they're not chained to each other in the first stage. Sorry? Ready state? I've just said it's the same. I just imagine that you manufacture an ancilla and then you write and you say, please send me 5 copies of this ancilla. So they'll all have the same ready state. Okay, so now we want to redo the calculation with the ancillas. We see that nothing much will happen. So let me rush a little. Well, looking ahead, but at least we'll get through this first and second. We may not really get to completely do the general case, but let's see how we can go. So in this one, we started with the particle in beam 0. Now we have to have, our history has to be represented in a more general way. We have to have the 2 ancillas. So far, they haven't really done anything. We might not even have, in principle, manufactured them yet, but we have to do them very quickly in the time before the particle gets from here to here. So anyway, so we have, let's imagine we really set it up with all the ancillas. So they're sitting there just in their ready state. Now what's the amplitude for, oh, I really should have done, but I didn't. I said in words, but I didn't write in formula what the ancilla does. But I said just to save time, I won't bother to write it now, but it just copies what the history did. That's why it's like a controlled knot gauge. Anyway, we'll see it in action here. So now there's an amplitude to go, if we're interested in the same history here for the particle, then the first stage is just to pass through this beam splitter device. The ancilla hasn't looked at it yet. So all that happens with amplitude, the same amplitude A10 is here. The ancillas haven't been brought in. Yet now the ancillas look at, now we get to the stage where they're coupled in, and the particle has done what it's done. In the first ancilla now, since the particle was in beam 1, it makes the transition to state 1. The second ancilla hasn't done anything yet. The important thing is that this amplitude is 1. This is what I mean by calling it a controlled knot gauge. If the particle was in beam 1, which it was here, then the ancilla, the first ancilla, will make a transition with amplitude 1 to a state 1. If it had been in beam 0, the ancilla would have made a transition to beam 0, its beam 0. You look unhappy. That's the second ancilla just sitting there waiting to just sitting. Then it's just the same, more of the same. The ancilla, now in the second stage, the particle, in the next stage, the particle, the photon, encounters the second beam splitter. And so where am I? So now we've said that it goes in the 0 beam. The first ancilla has already done its work. It'll never change again. Now because, and the second ancilla is still just sitting there, the amplitude for that to happen is A01, because all that happened at this step is that the particle made a transition from beam 0 to beam 1, right? And now finally, I'll probably afford to erase this here. Yeah, I can afford to erase all of the homework. Finally, in this stage, the ancilla copies the particle. So finally, the second ancilla comes in. The particle has already done, it's in its beam 0, going merrily onward, never to see another ancilla. The first ancilla has copied what the particle did in the first beam, and first inter-splitter beam. And now the second ancilla kicks in, and it looks and says, aha, 0, so it copies that with probability 1. With amplitude 1. And that's the whole history up till now. Now I want to introduce, for future work, I want to introduce the simplified notation. You can see there's always going to be an R here, there's always going to be an R here. There's always going to be two sets of brackets. This is trying to emphasize what Urvashi asked about, that the two ancillas are not chained together. They each one have their own separate interaction with there's really two different ancillas. And this is left over from the original notation, but obviously I don't lose any information by writing it just in this way, leaving out the R's. Okay, so this is a shorthand for that history. That's the history. That's the only history that has a non-zero amplitude. I could have also computed the amplitude. There are other possible histories, like it came up in that question. For example, there's a history in which the ancilla incorrectly copied what the particle had done, but that's the way the controlled knot gate is defined, that will have zero amplitude. So I'm only bothering to save space and thought and so on. I'm not only bothering to write down the histories which have non-zero amplitude. and in this case, there's only this one. Okay. So the net amplitude, so I don't know what to call this. Let's give this a name, capital gamma, because it's the history of the big system. And the amplitude of gamma, as we see here, capital gamma, is equal to minus. The only important things were this A01 and A10, and they're the same as for the system before we messed with all the ancillas and so on. So again, it's minus 1/2. And so the measure of that, so now we'll have a final step, stage 2, stage 2 of the measuring process. In this case, it's trivial because there's nothing to forget, nothing to process, no interferences to worry about. So anyway, so I've introduced a simplified notation, which we'll be using from now on. So now comes stage 2, which is the readout stage, which means we couple the ancillas to some sort of last ancilla, extra ancilla, which is the thing that clicks or doesn't click. And so in this readout stage, it's looking for a click. So yeah, let me just write this sort of. Now this readout ancilla, it looks exactly like the other one that I just erased. It has a ready state, and it has a 0 and a 1. I'll call this one click. And I'll call this, I don't know, mute or something. It doesn't click, and it does click. So we're looking for, if we get an indication that the event that we're interested in really did happen, if it sort of passed this filter, then we'll indicate that by the click. That it'll be registered as a click of this final ancilla. Yeah. Is there a question? That's right. Yeah. It's a basically deterministic yes, that's right. That's crucial. That's a crucial aspect of it. And as I said, I didn't go and make, which in principle I should, to make everything fully concrete, I should have modeled the coupling between I should have modeled the ancilla, not just as a black box, and I should have modeled the coupling of the ancilla to the photon, which I haven't done that. I've just said, oh, it's a C0 gate. However you do a C0 gate, you do this. It's not case 2. This is still case 1. We're still in case 1. So every case will have, the measurement will have, as I said, 3 stages. First stage, so we've done, first we computed mu. What we ran, that's nothing to do with the measurement procedure. That's just the number we're aiming to get. Then we started with the measurement. The measurement has 3 stages. The first stage is coupling all these ancillas, which we've done. The second stage, which is going to be a rather abbreviated, trivial version in this case, but will become very crucial when we come to the more general events. That second stage is what I called readout. That consists in coupling the ancillas to each other in a certain way and to the into the final the counter, let's call it, the final ancilla. So this is the counter. And then the third stage is again kind of trivial. Just look and see whether you got a click or you didn't get a click. You could, if you regard this as being a click, if you regard this as being a pointer, then you don't even need the third stage. But in a laboratory, of course, you would have to put some sort of photon detector or something here to see whether you got the click or you didn't get the click. So have we, okay. So, what happens in this final stage? It's again one of these controlled knots, but it's a much more complicated, much more interesting controlled knot. It doesn't just look at whether or not a particular history. It looks to see whether the history was in the event E or not in the event E. So that's what it's asking. It's sort of, in this stage, it's sort of let's say, listening for the event E. So it looks at the history. See, the ancilla now has remembered the history. Oh yeah, and I should say again, this stage, oops, photon, I've said it before, but it should be emphasized, that the photon is a spectator. This stage involves only the ancillas among themselves. So the ancillas have remembered what the history was, and now they just ask themselves, was it in the event E or was it not? In this case, if it's in the event E, which it is, I hope, yes, it is the history that defines the event E, then we make a transition to 1, 0, U. Oh, I see it. Sorry, I got the I used a different notation for the counter. I called them up and down instead of 0 and 1. So just hopefully it makes an improvement to the notation. So in this case, it looked to see this was in E, and therefore the ancilla goes to U. If I had put here something different, like if this had been 0, 1 instead, let's say 0, 0, 0, and this would be 0, 0, the ancilla would have looked, say, uh-oh, no, 0, 0 is not one of the histories I'm interested in. It would have made the transition to down. Maybe it's not 100% clear, but we'll see it in action when we come to the two ancilla. So this is the net history. The amplitude is still minus 1/2 as always. And so, and I'll define the click event that just says, it's the event that says ancilla counter in mu, in B mu. So that's the click event. This is the only. Now what we want. This is a little subtle in a way. We want the measure into the combined setup of the click event. Well, the click event is itself a set of histories. So we use it's just the usual rules for computing the quantum measure. But in this case, there's only one history of non-zero amplitude in the click event, and that's the one that we've done here. So the measure of the click event itself is minus the click event itself. When we compute it, we square amplitude 1/2. And so the measure of the click event itself is 1/4. And so in this case, we find that the measure, and now I want to make further. I use U for, but I have it backwards. Thanks. Yeah. Exactly wrong, yes. So U is the click, and D is the mute. Right. Thanks. And one other thing that I should do in a way of notation, I've just called this, I distinguish mu naught from mu, but it's important to realize that this mu it depends crucially on how I set how the ancillas are coupled and so on. And the whole thing is designed to look for a particular event E. So I really should put a subscript E on mu. So it's the quantum measure when we have set up a filter or detector looking for E. And what we found is that the probability, which is in this case interpretable as a probability because it's one of these instrument events or terminal events, that the measure of the click for the E counter, the E detector, is in this case equal to mu naught of E, both of which are 1/4. This is the basic result, although it's really kind of trivial in this case where we had only one history. Now, hopefully, maybe I'll just wait a second in case someone wants. One other notational thing. I should define the click. I've defined the click event in words. I can define it in symbols this way, now that we have this notation. The click event consists of a whole bunch, like any event, of a whole bunch of histories, and I can illustrate what histories it is with these these wild cards here. So a history gamma is in, this is a history, using that notation we've established. A history is in the click event if and only if the click, the counter emerges, the counter ancilla emerges in the being U. Okay? So that's, so anything that, whatever you have here, 0 or 1, 0 or 1, anything, as long as there's a U in the end, that's the click event. That's the event whose measure we're computing. Yes. What will always come out to be unity? You mean this will always come out to be unity? Yes, this will always come out to be unity. That's right. However, when we come to two histories, the next case, then there's going to be a further processing stage as part of this readout stage. But that's right. Then there'll be some there'll be something happening in between here and here, which is crucial. So I just give you a second to take that in before I erase it, and then we'll do the case of two histories, and I don't even know if it's, well, see what we can say about N histories. M histories. No. K histories, anyway, some number, neither M nor N of histories. Or was N the number? Anyway, we'll see what, probably not. See if there's, it's a shame, okay, well, anyway. So let's do the case of two histories. We're doing this case. Try and go through the same steps. Now, fortunately, the first two things that we did, first we computed mu naught, the measure that we're really trying to reproduce or ascertain in the lab. And so in that case, I think we've seen it enough. We can just take for granted what it is. And the thing that we learned, the first stage of coupling the ancillas to the system is unchanged. It's only in the second stage, the readout stage, that we have to change the protocol depending on what event we're looking for. So the first stage is just for the ancillas to get into their memory what the history was. So I'll just shortcut. I mean, I won't repeat all the steps. I think you'll agree that what I'm writing down is what you would find if you went very carefully through every successive stage of the process as we did before. So this is the amplitude of the history 001. What we saw is that even in the first stage of coupling in the ancillas, all that happens is they copy what the history actually was, and the amplitude, because these C0 gates don't bring in an amplitude, or they bring in a global amplitude, which in the end will drop out, we don't have to worry about it. These are essentially the same, and in this case it's A10 times 00 because it went, I mean, I write these in the usual way from right to left for the transition. So this is the transition from 0 to 0, and this is a transition then from 0 to 1. And that's equal to, if you look at it, one reflection and one transmission. So it's equal to just I over the square root of 2, 0, 0, 1. So 0, 1 transmission, and then 1 reflection here. Okay. Anyway, we've seen that many times. And then there's the amplitude. In this case, there's two events that two histories we're interested in, which the other one was 0, 1, 1. That's its amplitude for the pure system is the same as the amplitude for the more coupled ancilla system as 0, 1, 1, 1, 1, which is A1, 1 times A1, 0, which is I over the square root of 2. So it turns out in this case that the two amplitudes are equal. Therefore, looking at just the first column, mu naught of E, so what do we have here? We have two events, both with the same final beam, so they interfere. So the rule is, so we can write it in two ways. We can write it as I over the square root of 2 plus I over the square. Add the amplitudes first, then square, and that equals 2. Or if we wanted to expand it out, just to remember the general form of the decoherence functional, I over this, we could expand it out, and we'd have twice the real part of I over the square root of 2 star times I over the square root of 2. Again, it's just an identity. I'm just sort of remembering why we get this three-slit sum rule. So either way, it's just the answer is 2. Right? So mu naught, the important thing is that mu naught of E is equal to 2. Was there a question? Oh, I left out, thank you, yeah. Should be 1 by root. I mean, I've left out a factor of 2 everywhere. Yes, you're right. So that's so. What happens? I guess I get a 1 here. Okay. Good. Now, mod squared. It'll always be positive. The quantum measure is always positive because in that sense, it's like a probability. It's unlike a probability in the sense that it can exceed 1 when you get a sufficient. And I thought this was an example, but now we see it's not quite an example. It's just saturating 1. Right, this should have been 1 over square root of 2. Okay, now I probably, well, we'll see whether I'm debating whether to keep the error or try and correct it on the fly. Anyway, now the important new thing that happens here is the readout phase, coupling to the counter and the coupling of the ancillas to each other and to the counter. So far we have arrived at this. Now, if we were to do what I said before, just look separately at each ancilla, then we would destroy the interference that we're looking for. So we can't do that. What can we do? Here's a method that we can follow, which was found, as I said, by Alvaro, and Mosota, and this is what we do. It goes by the name. In this case, it I think kind of is a quantum race, but in general, which we obviously won't get to, it'll be a generalization of the quantum arrays. So let's see if we can do this efficiently, rapidly. 0, 1. So here's the ancilla. Now I've brought in the counter ancilla too. So this is and I'm looking at this particular history. So what will happen with this history, and then we'll see what will happen with this history. So what I'm going to do is design something, and again, it's an interesting homework to make a real life optical model of how to do this. I have no idea direct how to do it, but we design something in the spirit that you can design any unitary transformation. We design something which makes when this ancilla history, remember in this stage, the original photon is now a spectator. Really everything that's happening happening just with the ancillas. So this upper line will never change, but it's still there, so I leave it. But we'll take, instead of making this what it did before, say, which was to say, oh, well, this does belong to the E. This is one of the histories we're looking for. Before I made it make a transition to U, which is the click, with amplitude 1. Now I make it with amplitude 1/2. And so what else does it do? Instead of that, with an equal amplitude 1/2, it goes, still says yes, I like that one. So I'm going to click, but I'm going to make it mix with the other history in E. So the two histories in E that we're looking for were this one and this one. So I'm going to make it, I'm going to mix it. And now I'll do the same. You can see what's going on. I'll do the same for the other. That's how we would continue with this history. Now with this other history, it's the same as the same. There's no room to draw it underneath. Draw it side by side. This is 0, 1, 1, 1, ready. And it makes the transition with probability 1/2. With amplitude 1/2 to 0, 1, 0, 1, 1. The top never changes. The particle is now a spectator. But here, what was the other one? Well, so first of all, itself. Yes, I'm going to click. And then with probability 1/2, sorry, I keep saying probability. With amplitude 1/2, it'll go to the other one, which was 0, 1. Okay, I got it right. Oops. So the thing to notice are these. These are the things that you wouldn't obviously think of. The fact that I only with amplitude 1/2, this is also 1/2. Does it just mindlessly say yes? It also mixes with the other ancilla set of beams that correspond to the other history. So in general, it's going to mix with, if there were 3 histories, it's going to mix with probability 1/3, with amplitude 1/3, each of those. So the ancilla states are getting mixed up, all with positive and equal amplitude. That's the protocol. Yeah. Yes. Well, not maybe, hardly. We're not. It's clear that this is looking for E, right? So it's only going to click when the histories involved did belong to E, when the histories that the ancillas remember were for the event that we're looking at. However, if we separate all the, if we didn't do the second line, then we would, as I said a couple of times, we'd destroy the interference. So I think the way to see this, the way to see this is to go, which I was certainly going to do, is compute the measure now of this set of histories, the measure of the click event. And when you compute it, you'll say this will cause the amplitudes to mix with each other in such a way that the interference it'll mimic, in the calculation, it'll mimic this rule of adding the amplitudes first and then squaring. If I hadn't mixed them with each other this way, it would have been like squaring and then adding the amplitudes. That's the best I can say now. No, it's not circular reasoning. It's a protocol. Now we go and we do what we should do, but I'm really out of time, unfortunately. What we have to do now is compute mu E, meaning mu with this setup of the event click. And the event click is still exactly the same event that we're talking about. When you compute it, you'll see that the amplitudes do add up in the way that they're supposed to. So I don't see that it's circular. It was kind of reverse engineered, if you want to say that, but that's fine. Yeah, we know the answer we want. Um, I agree that it's reverse engineering. I disagree that it's circular reasoning. This is not saying that out of first principles, I can just sit as a philosopher and think, what should be a detector for this event E? But I know what the answer I'm looking for, and then I design a detector that does that. I don't see anything circular about at all circular about that. Yeah. Yes. Yes. Yeah. It always copies first. So that's the first step, and then it goes on and mixes. You could say that it was, but there's only one thing to mix itself with. Oh no, it has to. This is the only protocol I know that will give that will end up with the probability. Yes, exactly. It was trivial. There was only one, and so I had a 1/1 going to there. If there had been three histories, then I would have had three things, and I would have had three possible transitions. Each one would have an amplitude of 1/3, and so on. So this, yeah, so the single history case is a special case of the general procedure, which is more or less apparent already in the two history case. There's no, yeah, so I don't know a principle why this works. That's why I said I can only partly give a sort of a complete full motivation for this. The statement is it works. You might, if you want to read up on a quantum eraser, you might ask yourself, why does it work? And how does it work? And that would shed some light. Because that's, in this particular case, that's essentially what's going on. So I guess I really should state the results, and then I really have to quit. So I wanted to, can I take like another, how long? 2 minutes? I wanted to show schematically what's going on in this case. So there's a calculation. I mean, we've set everything up. We know the rules for computing the quantum measure. So instead of going through the calculation, which would have been a much better thing to do, let me just state the answer, which is that this event C consists of, in this case, it consists of four histories. This may help also to illustrate 0, 0, 1, 1, 1 here. 0, 1, 1, 0, 1. Probably some people can't see this, but 0, 1, U, and 1, 1, U. Okay. It turns out all of the four have the same amplitude, which if I made the same factor of 2 mistake here, if I correct it, I probably have to divide everything by the square root of 2, but never mind that. And you add these all up, and you get the desired answer. So mu e, again, you find that mu e of click is equal to mu naught of the event. So we check this. I think in my notes, each one is off by a factor of 2 now, but in any case, they're equal. So the only thing that I really didn't get to, there's one crucial point which I haven't yet been able to illustrate and won't be able, oh, that was we started late, I guess. So, which I unfortunately won't be able to illustrate properly, which is the rule that events with different final outcomes don't interfere enters here crucially, which so far it hasn't in the previous calculation. I want to just make a picture. I won't draw the picture here because half the people won't see it. So let me draw the picture. Let me try and just indicate pictorially what's going on. So schematically, what's going on is we had the system. I don't know how many. There were only 2 beam splitters here actually. So this is the system, the original system. Then we have an ancilla that couples in after the first beam splitter. So I'll show the coupling like this. Just try to show the coupling like this. Here's the first ancilla. This was 0 actually. This was the ready state for the first ancilla. After the coupling, the ancilla copied really what the particle had done, and it just goes on. In stage 1 of the process, that's all that happened with that ancilla. Then there's a second ancilla that comes in at this stage, which is, now it looks after the photon emerges from the second beam splitter, it looks as a second ancilla. It doesn't care about the first ancilla, so I'll sort of make a broken line here. But it cares very much about what the particle was doing after emerging from the second beam splitter. And so it has its ready state, and it comes out either in 0 or 1. Okay, so far I have 1, 2, 3, 4, 5, 6 beams in which the things can emerge. And then in the final, that was kind of stage 1 of what I've been calling stage 1 of the protocol. Stage 2, remember the particle is now a spectator, and the ancillas, however, are doing something clever and being coupled to each other, and also coupled to, you could actually split this into 2 stages, coupling them to each other, coupling to the counter, but it doesn't simplify, and it looks slightly more complicated if you do that. So here comes the counter. I need maybe another color for the counter. Stage 2, the counter, I called capital R, it's ready state. It comes out either in U or D. These come out in 0 or 1, according to our notation. Obviously, it doesn't matter what you call them. But the important thing is that now the particle is just going on it. So we have many histories, and a history will have a complete history now, including the counter and everything. We'll have in the end the particle emerging in one of these 2 beams. The first ancilla emerging in one of these 2 beams, second ancilla in one of these 2, and the counter in one of these 2. But each history will have the choice of each beam. The histories which can interfere are those in which the beam is the same. Each one of these 1, 2, 3, 4 beams are the same between the 2 histories. Only those can interfere. That's the crucial extra thing that you have to take close account of when you compute the measure. And I wish, as I said, that it would have been clearer instead of just saying this to go through the computation. But this is 4 ancilla beams and 2 counter beams. And then we get interference if and only if all the beams agree. That is 2 histories. Remember I introduced that symbol theta, if you remember, of gamma 1 and gamma 2, or gamma and gamma prime, I forget. It took account of that in the expression for the quantum measure. So when I did this calculation, it was important to see which ones interfered and which ones didn't interfere. And if you do it right, you get, if you take that into account, you get the result that I claim. So I'm afraid that's we're stuck for time. So the only thing more to say, so I didn't get, I won't even have time to write down the ansatz for the more general case, but it's a direct generalization of this ansatz. And I could mention that it has some ambiguity in, I mean, there's different versions of it, but the important aspects of it are, I mean, I wrote down a specific ansatz, but you could fill with that. But the important aspects of it that should not change are the ones that we've seen illustrated here. And I'll finish just by raising a question. I won't even have time to flesh out what I mean by the question, but you've seen it before. You may not see this, but I'll read it. It says, if the counter clicks, did E really happen? This is what kind of question that, ultimately, this is the question in the class of the ones what we would be able to answer if we really understood quantum mechanics. And this, there's a good reason to say that there's things indicating that the answer ought to be yes in this case. And in this sense, it's a minimally disturbing detector. But I'm afraid I don't have time to say any more than that.
Okay, so you have a question?
Yeah.
Initially, there was only one amplitude. You took the modulus square, the global phase factor, you get rid of that. Here you have two paths, 0, 0, 1 and 0, 1, 1.
Right.
For each amplitude, let's say for one there is a phase factor phi 1 and for the other path there is a phi 2. When you take...
Why would they be different phase factors?
Okay, the phase change is one of the paths, there is a phase.
But why would the two phi 1 and phi 2 be unequal?
Let's take there is only phase factor with the one path.
Yes.
So when you are adding both the amplitudes, and you...
No, when you say that just for one, you mean one of the phase factors is 1 and the other one is not 1?
Gave the, let's say one at 0 and the other phase change is with the one path.
But why would the two phases differ?
Okay, for both the path there is one phase change, right?
Yes.
So for one of the amplitude, there must be some phase change will attach with one path.
Yes.
Right? When you are adding both amplitudes and taking the modulus square, then how can you get rid of that phase factor?
Well, I'm not sure what you're asking, but I would just answer it like, right, I mean, if you have alpha plus beta squared, that's the same as e to the I theta alpha plus e to the I theta beta squared, right? Are you questioning whether this is correct, or are you questioning whether I should be writing equal? No, but why would it be just with one? What I'm saying is it's the same for alpha and beta. If you have a relative phase, then it will just change the measure. Yes. It might be, but I tried to design it so it wouldn't be. If it were, then we would certainly have to include that relative phase. It wouldn't fundamentally change anything. It would just mean that mu naught would be a different number now, and mu sub e of click would be a different number now. But they would still be equal. Oh, which case are we doing that? If we're doing case 2, then this was probably left over from case 1. But if we're doing case 2, there was a factor of 2 here. That was crucial. There's a factor of 1/2, actually. the other way around. This is important because it means that there's a loss of efficiency in the experiment. That because of it was 2, I wrote it correctly before, but I'm not sure, I might have written it incorrectly once. Because of this factor of 2, the measure you're looking for, the measure of the click is only half of the probability of the click is only half the measure you're looking for. So you've got a loss of statistics. So you need to do more repetition to get a given precision. What? Yeah, I hope I did it right, but the important point is it's the way that makes you lose efficiency if you use this protocol.
I guess we're running out of time. So let's thank